flipped classroom presentation for Further Maths Unit 5, Hypothesis Testing with Mann Whitney non-parametric test. We have already seen how to perform significance testing on the specified mean of any distribution whose variance is estimated from a large sample, use of the central limit theorem, the difference of two means from two independent normal distributions with known variances, the specified mean of a normal distribution with unknown variance, large sample using S squared as an estimate for sigma squared, or small sample using S squared and the t distribution. But there are many situations in which these assumptions are not justified, so alternative tests are required. These are distribution-free or non-parametric tests. And we're going to look at the Mann Whitney U test today. Situations may arise where we want to test for difference between the averages of two populations, but the data is not pairs, so we cannot use the Wilcoxon signed rank test. We cannot assume that the populations are normally distributed with no variances, and the samples are too small for the central limit to apply, so we cannot perform a Z test on the difference between the population means. We have two small non-paired samples from normal distributions whose unknown standard deviations cannot be considered equal. So we cannot perform a t-test on the difference between the population means. In these circumstances, a Mann Whitney U test can be performed. But the null hypothesis is that the two populations from which the random samples are taken are identical. That is, they're not simply a test to determine whether the averages are equal. So setting up the procedure for the Mann Whitney U test. So after setting up the null and alternative hypotheses, we rank all the values as if they are from the same group. Sum the ranks for each group individually, so sum of the rank for each one. Work out the test statistics for each group using the formula, so the sum of the ranking minus n plus 1 over 2. The value of U is the smallest value from the two groups of the U statistic. Compare the value of U with the appropriate critical value obtained from table 14 in the tables book. So the critical values in table 14 are for the upper tail and are included in the critical region. That is, the upper critical region is U greater than or equal to UC critical value. They are calculated using the normal distribution with mean mn over 2 and variance m plus n plus 1 over 12 distribution, which is the appropriate distribution for U when m and n are large. At least 1 should be greater than 10, but the distribution is still used for smaller values. The lower critical value is given by mn minus UC, the critical U. There are alternative formula for U which you might find in some sources. So let's have a look at an example. A supermarket fruit manager wishes to investigate the quality of bananas. Bananas are either delivered chilled from a source or stored at 10 degrees from source. The times to over-ripening of a random sample of chilled bananas and of a random sample of stored at 10 degrees bananas are obtained, and the rank values are given in the table. So rank 1 indicates that the banana was the fastest to become overripe. So they were all originally put together and ranked, then put back into their separate grouping. The supermarket fruit manager believes that chilled bananas become overripe faster than bananas stored at 10 degrees. Carry out a Mann Whitney U test at the 5% level of significance to investigate this belief. interpret your conclusion in context. So we are testing that the samples are taken from identical populations, that there is no difference in the means, against that the samples are not from identical populations. That is, on average, chilled bananas overripe faster than bananas stored at 10 degrees Celsius. So it's one tail. We want to check the chilled bananas overripe faster than the other ones. So it's one-tailed. If we call them A and B, they're already ranked, so the sum of the ranking of A are those and give us 22. The sum of the ranking of B are those which give us 44. So the statistic, the test statistic for you is the sum of R minus n plus 1 over 2. So for A, the test statistic is 22, take away 5 times 6 over 2, giving us 7. For B, it's 44 minus 6 times 7 over 2, giving us 23. There were different numbers in each group. So we are looking at the smallest of these is 7, so U is 7. Our test statistic is 7. So we're looking at table 4, with M was 5, N was 6, and 5% level one-tailed. So one-tailed, 5%, there's different tables for each requirement. So one-tailed, M is 5, N is 6, so we get 25 as our critical region. So U greater than or equal to 25. Or, for the lower-tailed, it's Mn minus the critical region. So 5 times 6 minus 25 gives us 5. That is U less than or equal to 5 or greater than or equal to 25. That is the critical region. The test statistic U, which was 7, was not within the critical region, so we keep H0. There's no significant evidence at the 5% level to suggest that the population average time to become overripe is lower for chilled bananas. Another example. The LDL cholesterol level was measured for each of 16 males living in the USA in 2006. Of these, 8 had been randomly selected from males under 30 years and 8 had been randomly selected from males aged over 50 years. The age and the LDL cholesterol level is given in the table below. So those are the males, there's 16 altogether. There's 8 of them under 30 and the others are over 50. The LDL level is given below. Carry out a Mann Whitney test at the 5% level to investigate whether in the USA males aged under 30 years have on average a lower LDL cholesterol level than those aged over 50. So we want to check if the samples are taken from identical populations, that they are the same, against the samples are not taken from identical populations, males aged under 30 have lower LDL average. So it's one-tailed 5%. We rank all the LDL cholesterol levels. So those were the ages, those were the LDLs. So ranking them, 121 was the smallest and 259 was the highest. Sum the rank for under 30s and over 50s. So under 30s we get 40. For the over 50s, these ones, we get 96. So we need to work out the U, the test statistic. So it's the R minus n plus 1 over 2. So for the under 30, we get 4. For the over 50, we get 60. Pick the smallest, so U is 4. And we compare this with table 14, where M is 8 and N is 8, we have a significance level of 5% and it's one-tailed. So one-tailed, 5%, 8 and 8, and we get our critical region to be 48. And we check the smallest one, so Mn minus the critical region, which gives us 16. So U less than or equal to 16 or greater than or equal to 48. The test statistic U is within the critical region, so we reject H0. There is significance level at the 5% to suggest the average LDL level is lower for males aged under 30. Another example, high levels of impurity in an alloy are a concern to the company that produces the alloy. Two alternative processes, A and B, are used by the company for the production of the alloy. The production manager of the company, Jess, decided to compare the levels of impurity in 10 randomly selected pieces of alloy made by process A and 10 randomly selected pieces of alloy made by process B. She wished to choose one of these two processes for the production of alloy in the future. The results in suitable units of her investigation are given in the table. A higher reading indicates a higher level of impurity. So carry out an appropriate distribution-free test using the 5% level of significance to whether there is a difference on average between the level of impurity in the alloy made by process A and that in the alloy made by process B. So we are testing that the samples are taken from identical population against the samples are not taken from identical populations. Population average level of impurity is different. So it's a two-tailed 5%. So we're going to rank all the levels of impurity. This time I'm going to give 1 to the highest level of impurity, and therefore the lowest is 2.05 would be 20. Sum the rank for process A, so those are the ranking for process A, and we get 77. The ranking for process B, add them up, and we get 133. The test statistic, we're going to use that. So for A, we get 77 minus 10 times 11 over 2 gives us 22. For B is 133 minus 10 times 11 over 2 again, which gives us 78. The smallest of these is 22, so U is 22. Comparing that, table 14, M and N are both 10. Significance level is 5%. It's two-tailed. So two-tailed 5%. 10 and 10, so our critical value is greater than or equal to 76. Or the lower one, which is 10 times 10 minus 76, which is 24. So U is either less than or equal to 24 or greater than or equal to 76. So our test statistic is within the critical region, so we reject H0. There is significant evidence at the 5% level to suggest that there is a difference in the average level of impurity for process A and B. And that's the end of the presentation for hypothesis testing using the Mann Whitney non-parametric tests.